So welcome back for the second talk of the session by Alicia Castro, who is telling us about critical JT gravity.
Hi everyone, thank you for the invitation. So I will talk a bit about the second part of the title of this trimester, quantum gravity. This talk is based on that paper, which the QR code is blocked, but you can Google it. So let me, since I know that there are mathematicians here, let me just remind you what is the connection between quantum gravity and random geometry in a very general way. So quantum gravity, gravity, classical gravity describes the geometry of our universe, okay? And actually, general relativity uses Riemannian differential geometry in Riemannian manifolds to describe how our universe evolves, okay? At the level of a theory, of a physical theory, what we would like to do, which maybe it's very, I've seen it's very well known by mathematicians, is that you want to compute a partition function. And what that means in physics is that you actually want to quantize the theory, okay? So the way that you do it is that you want to sum over all configurations, and you want to, which in this case could be given by a metric, and you want to weight each of these configurations by some action, usually given by the classical action. So what this means, how this translates in terms of random geometry, is that you actually want to sum over geometries, and you want to assign, and you want to weight them given a probability distribution that is given by this exponential of the classical action. Okay. So this is where the random geometry arises when one is trying to quantize gravity. So our universe it's four-dimensional, 3 dimensions of space, 1 of time. It has a closed structure, which means that our universe is not actually a Riemannian manifold, but it's a Lorentzian manifold. And we have a cosmological constant. So there, G is Newton's constant, and lambda is the cosmological constant. So we have a non-vanishing cosmological constant, which we believe it to be positive. So what that means is that there is an homogeneous curvature in our universe. So this is very difficult. That's one of the main reasons why we haven't quantized gravity yet. So in order to further study quantum gravity, we got to simplify models, okay? So in particular, we can reduce the dimension of our space, for example, to dimension 2, okay? We remove the causality, which means that we're going to be working with Euclidean manifolds or Riemannian manifolds, and we restrict the curvature, okay? For example, to having a negative curvature, which means a negative cosmological constant. So one of these models that has these three nice features, which is not our universe, but is a toy model, is called JT gravity, okay? So now what I am showing you here is the action of JT gravity, okay? What this action has, the first term, so this one, okay? This is just, for physicists, this is the classical Einstein-Hilbert action in 2 dimensions. For mathematicians, this is actually just a topological term, is the Euler character. It's a fancy way of writing the Euler characteristic of a manifold, okay? And then we have an extra term. So this is what breaks the triviality of gravity in 2 dimensions, where in this second part of the action, I have a scalar field, so that phi there, it's a scalar field that it's coupled in a very easy, almost trivial way to the curvature of my manifold, and in the boundary, So remember, this is a two-dimensional manifold. In the boundary of this two-dimensional manifold, it is also coupled to the extrinsic curvature. Okay, so if you compute the equations of motion, okay, for the scalar field, actually what this implies is that this scalar field only acts as the Lagrange multiplier for this term in the curvature of the two-dimensional manifold, and this sets the equations of motion to be, well, curvature equals to -2. This means that this is a model that describes hyperbolic surfaces. Okay, and for example, the way that one can think about it, particularly for a surface that has one boundary, is an immersion of the Euclidean disk into hyperbolic space. Okay, so the interior in this blue curve is going to be M, the surface I am considering, and the boundary that I am considering is going to be this. You should think about it as a wiggly boundary that is very close to the boundary of hyperbolic space, or in this case, of the hyperbolic disk. Okay. So with all of these assumptions, with this assumption of the boundary and this action, this is what is called JT gravity. Okay. Yep.
So it's also true that K is equal to 1 due to the equation of motion?
No. So that's the thing. We in the boundary, this is going to be fixed by the equations of motion, but in the boundary, we're still going to have degrees of freedom.
But how do I see it from the acronym? Is it is it just obvious from the action that that phi doesn't act as a Lagrange multiplier at the boundary as well?
I mean, the equations of motion, you usually are gonna impose them, impose conditions in the bulk,
yeah,
but not in the boundary. Yeah.
Is there a question online?
okay.
No. So I guess that you need those accidents on the boundary to a well-defined variation principle in the back, right?
Yes.
Or that indeed the equation of motion for phi is R equal to -2.
Yes.
Otherwise, you wouldn't be there.
Yes. Yes, that's a technical way of saying it.
Okay,
Yes.
okay, thank you.
Okay. So then how would I compute the partition function for this theory, okay, for this action? So my partition function, a general partition function of this theory is going to have this form. So it's going to depend. So one should think about it as some hyperbolic surface, okay, with n of these wiggly boundaries, where the hyperbolic surface is really going to be this shadow blue surface. And what I want to do, so those are in the length of these wiggly boundaries, they are going to be these betas, okay, which are again the only degrees of freedom really in my theory. And if I want to compute these partition functions, then I need to do the path integral over the degrees of freedom of the metric, and I also have the degrees of freedom of the scalar field, okay, which is called the dilaton field, in case I say it in that way. And I'm gonna have my exponential of the minus action. So now what one can do is, as I told you, the equations of motion in the bulk are going to be r plus 2 equals to 0. Okay, so I can divide, if I write this action in this expression, I can actually divide my partition function into two parts. Okay, so I will have a part that depends only on the bulk, so on the surface, and a part that depends only on the boundary. Okay, because again, in the bulk, I have these equations of motion, so I can, in other words, if I integrate over this scalar field, then I can integrate over the scalar field in the bulk part, and that's just going to give me this condition. And but I cannot integrate this dilaton field in the boundary part. Okay, so in the boundary part, I will still have some degrees of freedom, some scalar degrees of freedom, and again, I have the extrinsic curvature that survives.
Is this some kind of center point approximation? Why can you use the equation of motion?
It is not subtle. It looks like a subtle point approximation, and that's just because I construct, well, the action is constructed in that way because the equations of motion are here, and there I just multiply by some scalar field. But it is not a subtle point approximation. It just looks like it because the action is very particular. Yeah. And I wanted to say too that what you have here in the part where you integrated the scalar field and you got the equations of motion, okay, it's still going to be this. You're still going to have this exponential of that S0, which is just, you can think of it as just the Newton's constant, okay? Multiplied, remember, this was just a fancy way of writing the Euler's characteristic. So you're going to get the exponential of some constant to the Euler characteristic. So what this gives you is that your partition function, okay, is going to have an expansion in terms of the Euler characteristic. So it's going to have some genus expansion coming from the bulk part, so from the two-dimensional integral. And then there's going to have some degrees of freedom that are localized only at boundary. Okay. So, and what I want to say is that here in the Euler characteristic is going to give you, an ordering of how much these surfaces weigh, okay, in terms of their genus and their number of boundaries, okay. So, for example, for genus equals to 0 and k equals to 0, and this k, is geodesic boundaries for hyperbolic surfaces, you can compute explicitly this partition function. I'm not going to say how to do it, but it's just something called, it gives you something called the Schwarzian action, okay? And that this is the Schwarzian partition function. It's called the Schwarzian because exactly the extrinsic curvature has a Schwarzian form, okay? And for genus equals to 0 and one geodesic boundary, which is this one, the ones that are not wiggly and are actually geodesics in the hyperbolic surfaces, you're going to have something called the trumpet. That's how this geometry is called. And you can compute explicitly also the partition function, okay? So what I mean by this is that you can actually write the extrinsic curvature and you can integrate that to compute the partition function exactly, okay?
Can you explain again what are geodesic and non-geodesic boundaries?
Yes, so the wiggly boundaries are non-geodesic. These are boundaries that are very close to the...
You want to compute these for any combination of geodesic and non-geodesic boundaries in principle?
No. These are only geodesic. What the Euler characteristic counts are geodesic boundaries.
Yes.
Yes. There's going to be an interplay between a geodesic boundary and a wiggly boundary, but I will come back to that. Okay.
Again, you do have to still sum over all the possible G's and K, no?
Yes,
Okay.
exactly. So I already gave you, I didn't tell you how to compute them, but I am telling you that the building blocks, so the easiest cases can be computed analytically, well, exactly, in physics. And now what I'm going to give you, it's the composition. So one can actually use these building blocks to compute any partition function, okay? And the way that you can think of it is that well, a hyperbolic surface can be decomposed with n wiggly boundaries, can be decomposed by cutting along geodesic boundaries, okay? And these geodesic boundaries split your surface between something that contains a wiggly boundary and something that it's just a hyperbolic surface with n geodesic boundaries, okay? So this is this decomposition is valid. You can ask me later when this is valid, but I am a physicist, so I'm going to assume that I'm doing all of the good things in the world happen to me, and I can use them for my theory. Okay. So if this is valid, then I can actually write this partition function in the following way. So I'm going to have my sum over genus, because remember I have the Euler characteristic. I have n wiggly boundaries, so I will cut along the n wiggly boundaries using geodesics, okay? So in order to glue this building block that is called trumpet, okay? So in order to glue the trumpet to a hyperbolic surface with n geodesic boundaries, I need to sum over the lengths, okay? There's a degree of freedom here. I'm going to have some measure, okay? And I'm going to have these building blocks, which are the trumpets, okay? Which I know exactly what their expression is. So this part, the reason why it is very nice to decompose in trumpets plus these hyperbolic surfaces with n geodesic boundaries is because we know how these behave, okay? And this is exactly Mirzakhani's work. Okay, so this is a very well-known way of decomposing hyperbolic surfaces. And this volume, it's actually, so the number of hyperbolic surfaces of genus G and n marked geodesic boundaries is actually just given by the Weil-Peterson volumes, okay? The Weil-Peterson volumes are some polynomials, okay? So in the lengths B1 to Bn. So if you give me the lengths of the hyperbolic surface your favorite hyperbolic surface, I can give you a number of how many hyperbolic surfaces with those lengths in the geodesic boundaries are, okay? Yep.
Why is the measure for integrating over the lengths be dV, not just dV?
Oh yeah, because you can glue the trumpet in any way. This trumpet is rotation invariant. So you can you have big ways of gluing the trumpet to the hyperbolic surface. Mm-hmm.
And does this expression with the Weil-Peterson volume follow from the definition of the JT action, or?
Yes. Yeah, so as long as this decomposition along the geodesics, it's valid for your configuration. Yes, this is the exact form of the partition function. Okay. So let me now tell you just a bit about these Weil-Peterson volumes, okay? The Weil-Peterson volumes are having studied a lot. And what Mirzakhani realized is that, well, they actually follow something called topological recursion. That means if you want to get some information about genus G, you can actually go back, trace it back to genus -1, G -1, G -2, okay? So you only need genus 0 and genus 1 information to recover the Weil-Peterson volumes of genus G. And so this is called topological recursion. And what Einart and Ogati did is that they actually, well, this sounds a lot like something that happens in matrix models, okay? So they wrote this topological recursion in terms of a matrix model. So if you have heard the JT gravity as a dual matrix model, this is really where it comes from, okay? It comes from the topological recursion of the Weil-Peterson volumes. A matrix model, in case you have never seen it, or you just need a refresh of what it is. So this these matrix models, so there's actually a random matrix associated with it. So it is a partition function where you want to compute your random variables are going to be random matrices. You have some probability, well, some weights for each configuration, which will go as the size of the matrix, exponential of minus the size of the matrix, and some potential. Okay. So in the case of JT gravity, this is a very complicated potential, but we know the form. And again, if you have heard that that JT gravity is has a holographic random Hamiltonian associated to it, you can really think about this matrix as that random Hamiltonian. Okay. I'm not going to work with this. I'm not going to mention the word Hamiltonian again. But my point here is that you can use the tools of matrix models to study JT gravity, because the partition function of JT gravity is practically just Weil-Petersen volumes, and they satisfy topological regression. Okay. So now this is how I'm going to proceed. I'm going to use tools of matrix models in order to study JT gravity.
You have to take a large MD, right?
Yes, and actually the form of the potential that we know is for a double scale matrix model. Yeah.
Sorry, the Z of theta here is the same as the previous Z of theta.
No. This is something else.
But can you relate the two?
Yes. So this also computes the partition function of JT gravity, but without averaging.
So the bracket Z here is equal to the Z we had before for one boundary. Or...
yes. So this complete thing with the brackets already is equal to the partition function of JT gravity.
Okay, great. With one boundary.
Also it's valid for n boundaries.
Okay.
Here I'm just writing the expression for one boundary,
okay.
But you can put any insertions of this operator here, as many as you want.
Okay.
Yeah. Okay. So I promised to you that I'm going to give you also some random geometry. Okay. So what I'm going to do then is to use the tools of matrix models in order to write JT gravity as a theory of random hyperbolic surfaces. Okay. So of course, to construct some random geometry, what I need to give it to you is a space of configuration. So we have the space of hyperbolic surfaces of genus G and K marked geodesic boundaries. Okay. And now what we need to do is to construct the probability measure on this space. Okay. And then I have defined a random hyperbolic random geometry for you. So what you do, what one can do to describe this, to achieve this, is to work with generating functions. So I am just transforming my problem of studying Weil-Petersen volumes. I'm just packing them in some generating function, which is one usually does in matrix models, okay? Where the generating function is a partition function of your matrix model. So I'm going to pack the Weil-Petersen volumes in this generating function. As you can see, this is a generating function. So I am using this kind, what seems like these dummy variables mu, okay, in order to just recover the Weil-Petersen volumes when I take functional derivatives of my generating function and set these mu's to 0, okay? I will explain what they mean. They actually have a physical meaning. Okay, so in the particular case of genus 0, so I can do this for any genus, but in the particular form of genus 0, my generating function can be written in terms of another ingredient. And this is called the string equation. We physicists call it the string equation, so that's why string appears here, but it's not dependent on string theory, okay? But the string equation, really, you can think of it as just a transform of the an integral transform of the genus zero generating function of your matrix model, okay? The string equation also appears in the matrix model when you're studying the topological recursion. So this is the solution to the Helfandicke equations for genus equal to 0 and also h bar or 1 over n equals to 0. So Larchen limit. Here, this is the string equation in particular for this generating function. So this is going to give you the Weil-Petersen volumes, at least of genus 0 if you include it there. These are the Bessel functions, okay? One of Bessel functions / modified Bessel functions. So you can really think of this as a power series expansion. And something very important in here, as you can see, in order to recover the genus 0 generating function of Weil-Petersen volumes, you really need to solve or find a zero of this string equation, okay? So this string equation needs to be algebraic. And in matrix models, well, this is a solution to the string equation, but in physics, in JT gravity, people call it a fancy name called the ground energy.
What is mu?
Sorry?
What was mu in the expression for the genus 0 version?
Mu?
The upper limit of the integral.
Yeah. So this is the solution to the string equation.
And so what is the relation between the solution of the string equation and these Weil-Petersen methods? I mean, how does the string equation know about?
Yeah, so you can see it as the radius of convergence of where, so this is a formal expression, this is a power series, but in order to compute something like the Weil-Petersen volumes, you actually need the radius of convergence of this power series. Okay.
Okay. I mean, my question really was about, so if I look at the expression for the partial function, so this is something about hyperbolic geometry. So there are some hyperbolic surface with a certain number of genus and functors. How is that information encoded in the string equation? Because you are recovering the partial function by knowing the solution of the string equation.
Yeah. It is, well, the answer from my point of view is that I don't know. Because I am using, so when you translate remember what you're translating is to arrive to a matrix model is the topological recursion of the Weil-Petersen volumes. Not really, you're not really translating all tools from hyperbolic geometry. It's just the topological recursion that it's written in here. So I cannot tell you, there is not a clear understanding if this mu, if this solution to the string equation has has an interpretation in terms of the hyperbolic surface. Okay.
For any genus, do you have similar expressions for F?
Yes. Since these Weil-Petersen volumes satisfy topological recursion, you can write the expressions for everything, for all genus that you want. Here I am just writing for genus equals to 0 because that's all I'm gonna do. But yeah, you can generalize to genus bigger than 0. And the expressions are in the paper. Okay. So with these tools that I introduced, from matrix models, so with the generating function, in particular the generating function of genus 0, and the string equation, I'm going to construct this probability measure. Okay, so I am going to write the probability measure on this space of hyperbolic surfaces of genus G and k marked geodesic boundaries. So I'm going to have the generating function of genus G weighting this, well, because here there is where I have the Weil-Petersen volumes, okay? And this is the way that if you have never seen this, is you just think of what do I need to integrate against, okay? So this is exactly what you need to integrate against any quantity in order to get something that it's it's well defined and that it's going to give you an integral of 1 if you integrate over the whole moduli space of stable surfaces. Okay, so this is at least a part of the probability measure of a well-defined probability measure in this space. Okay, so I'm not going to go further into this probability measure. What I want to show you is that having these tools from matrix model of the generating function and the string equation. So actually, just by having the string equation, you're able to construct the genus 0 generating function, and then you can construct the probability measure, okay, in the space of your genus 0 hyperbolic surfaces.
Sorry, I'm just a bit confused here. So the probability on the left, it just depends on L1 and K. But on the right, there seems to be a dependence in mu. So can you?
Yes. So you have to integrate over the mu's.
Okay.
Yes, I am not writing it. Sorry, that's the currently. Yes. Yes, this is just the part that I want to show it to you. Yes, but there's also going to be a Val-Peterson measure there. There are going to be a lot more things, okay? What I want to show you here is that, you need the string equation, and you can interpret these dummy variables that we introduced in the generating function. Actually, they are going to weight how much these geodesic boundaries contribute in your probability measure, okay? Because they are multiplying. For each smart geodesic boundary, you have a mu of the length, okay? So you have this function there proportional to the probability density, okay? So you can really think of these mu's as some weights, as some probabilistic weights that are attached to each of the geodesic boundaries of your hyperbolic surface. Okay, don't worry, I am gonna elaborate. The rest of the talk is just elaborating on this point. Okay, so now with these tools coming from matrix models, we can re-express. Okay, I am just gonna re-express the known partition function for JT gravity in something that looks more like a random geometry. Even though it already looks like that here because you have the Val-Peterson volumes, okay? So I'm just reminding you here the expression for the partition function. So now I'm gonna also reduce my problem to having only one wiggly boundary. So this n, remember, is a number of wiggly boundaries. So the number of trumpets, you can also think. So I'm just gonna write the same expression for one wiggly boundary. This is how it looks. So again, you have your Val-Peterson volumes, okay? But now with, in principle, only one marked geodesic boundary. And you have to attach a trumpet. So now this is the expression that I'm going to try to rewrite in terms of the string equation, okay? So these two coming from matrix models. So my string equation has this form. So let's go back to it. It has one part that is just a power series with some coefficients that are constants. They do not depend on anything, okay? These are just multiples of pi. And it has a part coming from this second term that has the dependence on this weight, on this probabilistic weight it's attached to geodesic boundaries of length L, okay? So, and the way that it looks in the power expansion is just as an integral, okay? It's just going to be some integrals of this function mu of L against some powers of L. So if you don't like the expression with the Bessel functions, this is the equation, the appropriate equation for in a power series. If you know a bit more about hyperbolic, well, moduli space of stable surfaces, these are exactly, these gamma k's correspond to the KdV times, or at least these ones are some multiple of the KdV times for the Val-Petersen volumes, okay? And these TKs are gonna be some deformations of those KdV times, okay? And these are exactly coming just from the dressing, from putting additional weights on the geodesic boundaries. Okay, so the string equation looks this way, so that's why I'm gonna call it, these ones I call the pure JT gravity times. That means that there is no dressing, there is no dressing from mu in my hyperbolic surfaces. These are usual hyperbolic surfaces, and I'm gonna have my defect or brane times that are gonna be deformations of that pure JT gravity. And from matrix models, okay, so the reason why I chose just having one wiggly boundary is that from matrix models, this is a very easy expression for the partition function, okay, a genus 0, and it's just can be written in terms of these the inverse of that string equation, okay. So if I have the string equation, I can compute the whole partition function of JT gravity with one boundary using only this expression. So in matrix models, so in case you have seen this, I mean, in matrix models, one can think of this U or the string equation. Remember, there was some Hamiltonian, okay? So one can think of this U actually as some potential in the non-quadratic part of the Hamiltonian, okay? And really what you're computing here is just the thermal partition function. So you have here some energy, some Hamiltonian multiplying the inverse temperature. So thinking about in statistical physics. So this is where this expression comes from. So now let me go back to my partition function for JT gravity, okay? So I told you that you can write it in terms of the string equation, and remember the string equation is equivalent to the generating function of Val-Petersen volumes, okay? So that allows me now to write this partition function at genus 0 and one wiggly boundary as a sum over this. So here I have a sum from k equals to 0 to infinity. So this sum is going to translate to the partition function, also at the level of this. So what more than the analytic expression of this, I want you to pay attention to the form of this expansion, okay? So what does K represent? I already fixed the genus, okay? The only other degree of freedom that I have is the number of geodesic boundaries, okay? So, but remember, I also fixed the number of wiggly boundaries, okay? So here is where you can see the difference between these wiggly boundaries and the geodesic boundaries. The wiggly boundaries are these blue ones I already fixed that I want to just look at hyperbolic surfaces that are going to have only one of these, okay? So the first contribution, so genus 0 surface that has one of these wiggly boundaries is going to be the hyperbolic disk. So the first trivial example, almost trivial example that I show you. The second one is going to be now a trumpet, okay? So it's going to be something that has one of these wiggly boundaries, a hyperbolic surface, but it ends in a geodesic boundary, okay? And it has nothing attached to it. Then here there should be no holes, sorry. But then there's going to be these surfaces that we can imagine more clearly from the previous expansion of the JT gravity partition function. So I have a genus 0 hyperbolic surface where I cut along a geodesic boundary and then I glue a trumpet. But what comes naturally from the matrix model, from the string equation, is that you will have these contributions, okay? So where you have a hyperbolic surface with k plus 1 geodesic boundaries, and you only glue a trumpet to one of them, okay? And all the other ones are still these dressed boundaries, okay, with the weight mu. That again, when you are integrating over moduli space, you will actually have to consider the appropriate measure with the Val-Peterson volumes, considering these extra boundaries. Okay. So what people have done in JT gravity, well, mostly of what people have done in JT gravity is only consider this type of this part of the partition function, where you glue a trumpet to each geodesic. If you have a geodesic boundary, you glue a trumpet to it. Okay, but these ones that again come naturally from the matrix model, they have not been considered. Well, they have not been considered in their generality until this work. Only a couple of them literally have been considered until this paper. So people have thought about these two cases, something called the FZZT brane and the end of the world brane. Okay, so what people were thinking really is that we can go to string theory. Okay, so surfaces, when you think about them as some world sheets, okay, as some string moving, and this is the video or of how they propagate, and they can end at some places called branes. Okay, these are these planes. So yeah, so you put certain kind of boundary conditions, and what I want to say is that they correspond to this weight, okay, to this mu function, to this particular form of the weights, okay. So this is what people have done before this paper is consistent with this formulation of coming from matrix model with the string equation, with the well-defined probability measure, etc. Was someone gonna ask?
Yeah. What is the difference between the FZZT brane and the end of the world brane?
In terms of string
Features?
theory, they are just different boundary conditions.
So but in terms of features, I mean, it's just the same geometry.
Yes. Well, okay, at least in my understanding, they would be very similar geometries here. But people draw very different geometries when one is considering this picture, okay, where this hyperbolic disk is really counting all contributions from all the defects. Yeah.
There's still something I don't understand about this mu. I thought you introduced it as a dummy variable, which was just to be integrated over. And now you are saying that taking a specific value of mu is giving a different model. So can you compute stuff at a fixed value of mu, or do you only get stuff integrated over mu?
Yeah, so in principle, when one is when you're computing things from when you're computing when you're working with the Val-Peterson volumes and you want to re-express the topological recursion in terms of a matrix model, you have to introduce these variables to produce a generating function. So yeah, they looked like some dummy variables that you have to integrate over. But what I am telling you is that actually, if you set some specific values for that mu, then you will get a generating function, okay, that has the Val-Peterson volumes here multiplied by something, and that corresponds to some hyperbolic surface dressed with a statistical model. Okay. Okay. I have until 1. Okay. Okay. So again, what I want to very briefly, again, I want to tell you the string equation is enough to do anything you want to stage in a 0. Okay, so input string equation. You can compute the partition function and also some Laplace transform of the partition function, which is called the density of states. Okay, just like in thermodynamics, in statistical physics. And yeah, and these have already been studied before. So now let's go to actually like the main part of the talk. So this is the talk, it's critical JT gravity, okay? So what the idea here is that, well, since hyperbolic surfaces can also be described in terms of these string equations, okay? And for string equations have been studied in matrix models, but also in maps, okay? So what of the results that we know in maps can be generalized to hyperbolic surfaces via the string equation, okay? And one of the easiest things to do is to just look at these results from macroscopic and Mon, which they categorized maps according to the value of the first derivative of the string equation. Okay, so what this means is that if one does a Taylor expansion around the solution to the string equation, the first term, the constant term, is always 0 because it's a solution to the string equation. The second term, which will be linear in U, which is a formal variable, is going to go proportional to the first derivative of the string equation, evaluated at the solution. There can be some non-analytic terms, and then you will have the quadratic term in the formal variable, okay? So then, depending on the first value of the first derivative, you can have different cases. So you can have the subcritical case, which is when this derivative is different from 0, so the linear term is going to dominate. You can have generic critical, that is when this derivative is 0, but there are not non-analytic terms, so then it's going to be, the first contribution is quadratic. But there is also something called a non-generic critical. That is when there are the non-analytic terms here in the middle are the ones that will contribute the most to your string equation. And what this means what this would mean now for JT gravity or for hyperbolic surfaces is that, well, I can ask the question then, the only thing that I can tune is these weights, is this the value for mu. Everything else is fixed, okay? So does there exist a weight, okay, such that my string equation for hyperbolic surfaces with defect behaves exactly on this way? So it behaves as an non-analytic power of the formal variable u, where this, remember, this alpha is between 3/2 and 5/2, okay? And the answer, which it's formally proven by Timothy Bode and Piotr Koster, but they haven't published it. I borrowed their result to do all of this, but I'm going to give you the physicist argument of why this is possible. Okay, but the answer is yes. So then my work was, well, okay, if it exists, if the answer is yes, what does it mean for JT gravity? Okay. So the argument is more or less like this. So you have the string equation. It is very complicated to do this proof compared to the maps case, because in the maps case, the first part, your Bessel function J1, is actually just a U. It's the linear part, okay? So that's what differentiates maps from hyperbolic surfaces, that the Bessel function J1, it's just a linear term, okay? So it is easier to prove that, but well, one can propose a weight that has right asymptotics, okay? And try to find some values for these constants kappa and lambda, which are free parameters, in order to achieve this criticality. And what you do is that you use properties of the Bessel function. That's all I'm going to say now, but the answer is that yes, there are some values for this kappa and this lambda, such that you will reach some non-analytic powers. The leading order of the string equation is some non-analytic power, okay, of u. That is between 1 and 2. Now you can also compute the disk function, okay? So the disk function is the generating function of, in this case, hyperbolic surfaces with one marked geodesic boundary, okay? Just like you do it with maps. So this is, I'm just giving you the analytics expression. You, again, string equation is enough. And you obtain, the result that you obtain is this one. So you obtain that the dependence on alpha, which is this parameter between 3/2 and 5/2, it's included here in the power of the length of the geodesic boundary. Okay, and there are some constants in front of it. And if you have seen this, maybe this will ring a bell. This is actually what happens for random planar maps with large faces. Okay, so this is the behavior that has been seen for maps. Okay, but now we see it for the string equation of hyperbolic surface. Actually, there is an even. You can look at the whole thing, at the whole expression for this function, and you can find here, if you compare this expression with the weight, with the original form of the weight that I proposed, you can see that this function is proportional to the weight, okay? For certain values for the value lambda equals to square root of E mu. And this is something that happens in the Owen model, again, in maps. So here I am just writing the weight proportional to this function. Now, if you have never seen it, this comes from the fact that when one is considering, it doesn't have to be a hyperbolic surface, by the way. I mean a map, but here I am drawing it as hyperbolic surface. But when one is considering a map with a loop decoration, one can change, in some cases, the loop decoration by a face decorated with the appropriate weight. Okay, and this is did I include it? This is exactly what was done in that paper, Borot, Boutier, and Guita. And so this is something reminiscent of the Owen model. But in this case, what I am describing here are hyperbolic surfaces. So I would like to think of this solution for the weight that helps me to reach non-generic criticality as an Owen loop model. But now instead of having maps, you're having a loop decoration in a hyperbolic surface. So this is a proposed model that would describe these hyperbolic surfaces that reach non-generic criticality. Okay, that means that they have a certain weight that makes the string equation behave in a non-analytical way. Okay. Yeah, so the intuition about that is that you can consider a hyperbolic surface dressed with this loop ensemble, okay, where now the loops are going to correspond to just decorated geodesic curves. And your partition function, in principle, is going to look very similar to the Owen model in maps. But now you have, again, good that the other talk was before this one, because then now you remember that there was an n, okay, an n that can take values between 0 and 2. That is the ON model, the n in the ON model. You have here, I think this was called kappa, okay? So you have a kappa that was to the power of the number of edges, which is the length of the loop. So here is your kappa, is e to the minus x. And here is the length of the loop, okay? But now instead of summing over maps, you are actually summing over hyperbolic surfaces. So you need to have the appropriate measure here, which goes with the Val-Peterson volumes, and you have your weights, okay? This model is not solved. We didn't manage to solve it. So this is my main, the main thing that I'm throwing at you, because maybe one of you can tell me, or we can solve this model analytically. Here I am just telling you that this is the drawing, the picture of what it means to have a non-generic critical weight for the string equation of hyperbolic surface, okay? But again, I am a physicist, so what I am interested in is the partition function of these systems. So I tune, or I choose these weights that give me this non-analytic behavior. How is it going to translate into physical quantities? So the partition function, for example. So what happens is that now my partition function with one asymptotic boundary or one wiggly boundary is going to behave as beta to the minus alpha. So where alpha is a real number between 3/2 and 5/2. Now what you can do to compare it to some particular cases like the Schwarzian, so when you have no defects, nothing, when it's just a hyperbolic disk, okay, you have a beta to the minus 3/2. Okay, so this is a model which partition function moves away from the Schwarzian. And now in terms of the density of states, so that is the analytical expression. So now you will have a leading order of the energy to the alpha minus 1. Now again, to compare it to something you know, the Schwarzian is this behavior of square root of E. And this critical JT gravity, which again is hyperbolic surfaces dressed with some kind of branes, okay, go away from that square root of E behavior to something that it's a non-integer, non-rational power. Yeah, and actually this behavior, this E to the 3/2, this has been seen already by people studying the FZZT branes and end of the world branes. But these curves in the middle, this behavior in the middle hadn't been seen before. So these are some other universality classes actually of some quantum models that are dual to some JT gravity, well, critical JT gravity, which is JT gravity dressed, well, with some branes attached to it. Okay, the final thing that I want to say is, well, what does this non-generic criticality means in terms of random geometry? So one can compute the expectation value of the number of geodesic boundaries of a hyperbolic surface. And it turns out that this expectation value will go as some finite function over the derivative of the string equation, okay? And this derivative of the string equation is exactly what we're taking, well, what goes to 0 for the non-generic critical case. So this diverges, okay? So, but you can see that for the subcritical case, it doesn't diverge, it is finite. So you really have a phase transition at the level of the hyperbolic surfaces where for the subcritical case, you have a finite number of geodesic boundaries. And for the critical cases, you will have an infinite number of geodesic boundaries. And one can also compute the variance of the this is the length of the curves, so of the geodesic boundaries. And one can actually find again that it diverges for the critical cases. So what that means is that it's something very similar to to what we saw in the last talk, okay? So like in the ON model, there are some phases where you have very small loops, but now these loops correspond to geodesic boundaries, geodesics for the hyperbolic surface. Then there is some regime where they become large, but they don't touch each other. They are still far away from each other. And then there is a part of a phase where they actually start almost touching each other, and they are very, very long. But again, this is just drawings at this level because I haven't solved the whole model. So if you want to know, well, what is at the end, what is critical JT gravity? Okay, critical JT gravity, you can really think of it as a model of quantum gravity in 2 dimensions, where your space is a hyperbolic geometry, and there are these places where your space ends, but they are not any boundaries. They are specific boundaries for which the lengths of these geodesics want to be very big and very wiggly. Okay, and if you want to think of it in terms of the dual quantum system, it's going to be a quantum system that has that falls into a different universality class than the Schwarzian. Okay, or that has the density of states, the energy density goes as this power of the energy. So yeah, so I'm just gonna leave this here. So we still need a particular model of branes. So some branes coming from string theory, or a more physical insight into what these weights that I am choosing that give me the criticality actually mean in terms of some boundary conditions. From the point of view of the boundary theory, so we have some preliminary computation that suggests that this is the formation of the Schwarzian that corresponds to introducing a math. But that's still work in progress. The weights are something that appear naturally from the point of view of matrix models. So, and these weights can take in principle any value. So another way to use the weights is to explore things like factorization and some replica tricks. And of course, solving the hyperbolic ON loop model. Exactly. Okay. And hopefully prove something, some phase diagram like this, just like in the ON loop model in maps. Okay. So thank you.
Thank you. Any questions?
So perhaps a very stupid question, but let me ask anyway. So this alpha appears in these kind of boundary conditions or branes that you attach, right? So, but then from the point of view of the one-dimensional theory, say the holographic, the quantum field theory at the boundary. So these are just indeed some boundary conditions or defects that you can attach. And since I mean, alpha looks like a completely arbitrary parameter that you can choose. So it seems to indicate that in this boundary theory, you essentially have a lot of freedom for choosing your defects. So there is no constraint on alpha. Is it correct? Like, so does it mean that if I try to find if I try to classify admissible defects in this one-dimensional theory, I find a family, at least one family, that is parameterized by alpha? Or, in other words, I mean, do you know if there exists a classification of these defects? I mean, this is very kind of, I mean, perhaps not, but it's surprising. I mean, usually, when you classify defects in theories, I mean, you don't have like continuous families. I mean, it's
yeah, that's what I don't know. The answer is that I don't know. That was my hope initially. So I was hoping that there would be an entire classification and that I could match alpha with something that was a free parameter also in some boundary conditions or some family of branes. But at least I haven't found that classification.
So
Toward
in,
that
in
point.
other words, these curves that lie in the middle between two extreme values, these are not necessarily, we don't know if they are admissible boundary conditions.
Yeah, so
From the point of view of the one-dimensional theory, because
yeah.
I agree that from the point of view of just JT gravity, I mean, it's a brane that you can attach. That's fine, but I'm asking from the pure quantum
From the
theory-
Schwarzian, yeah.
from the pure quantum theory point of view.
Yes. So for what we have seen, this preliminary computation that we have, this alpha would actually be proportional to a mass. So then, yeah, you have a continuous value of this mass that you can, it's a massive term of distortion. But this computation is done, so you can do a lot of transformations to the Schwarzian action to put it in some very nice forms, respectively using the symmetry of the Schwarzian. And this interpretation in terms of the mass is actually in another coordinate system or in a transformed action which is not very clear if it is actually translates to a massive term in the original form of the Schwarzian. But yeah, there is that's true. Like from the Schwarzian point of view, there is also you can also deform it with a.
Do you know if there is a value of alpha such that the boundary for the one-dimensional theory is gapless?
No, I don't know.
Okay.
Yeah, that is something.
With just power law correlation functions.
Yeah, and no, we only computed just the density of the energy density at first order. So just to get the power of e to the alpha, but we didn't go further to actually. Well, we haven't gone further to actually study the structure, the rest of the structure of these quantum systems.
Okay,
Yeah.
thank you.
Other questions? I don't know, on Zoom? No? Maybe just a curiosity. In the slide, I guess it's more or less related. In the slide where you have different alphas and the color, I got confused how you pick up exactly this. Yeah, exactly. This value of the exponent, like what differentiate between
these, yes. So these alphas, so remember alphas are the powers of u in the string equation, the powers of u that go between 1 and 2. Okay. So it parameterizes all the powers of u that you can have between a linear and a quadratic term. And those are the values of alpha that appear in the powers of the energy. Okay. So just like from 3/2 to 5/2. Sorry.
But I have the full spectrum.
Yeah.
These
Yeah, not only these ones. Yeah. No, I just chose some values, but you have the whole
you have the
continuum, the number of theories in them. Yeah.
And you can't distinguish between them. I mean, you don't expect any.
No, yeah, you can distinguish between them. I mean, at least that's the. So that's something that we haven't figured out, right? Because on one side it looks like this massive deformation of the Schwarzian, but I mean the density of states in matrix models and also in statistical physics. I mean the leading power of E actually characterizes different universality classes of some quantum system.
So you expect that within this region 3/2, 5/2, there is actually different phenomena.
Yeah. I mean, in principle, from this point of view, each of these curves, like continuum number, would each of them correspond to a different universality.
Okay.
So yeah, that's what I can say.
This is only true if each of these values correspond to actually a theory that is gapless. Otherwise.
Yes, but at least, yeah. So I have assumed here for this that the theory is gapless. Yes. So if there's a gap, of course, this one, the density of the energy density won't look this way. Yeah. Yeah, so that practically means that I only have, I have E0 is
So
here
I'm confused again. So to compute that, like this formula, you didn't have to assume anything about the boundary. You didn't have to assume that the theory was gapless.
I assume that the fact that I can express this density of energy as E minus E0
Yes.
assumes that I am close to one of the ground states and that there is no holes in the middle. So if you want, from the matrix model point of view, this is the double scaled density of states. So I am really taking the ground energy and I am like zooming in just to look at the behavior very close to that.
Okay, so the prediction is that there should be really a one-dimensional family parameterized by alpha of say so conformal field theories, where this alpha somehow should parameterize some boundary condition or something like this, some deformation of these one-dimensional theories.
Yes, and this deformation could be seen as some mass insertion in the Schwarzschild.
Yeah.
So
In the bulk.
In the boundary.
But then in the boundary, you will not have power law. You will be away from criticality, you know?
Yeah, so what I am saying here is that I mean, this is seen as the Schwarzschild being the low energy limit of a CFT that lives in one dimension.
Yes.
So from that point of view, this would correspond to some massive insertions in that one-dimensional CFT. That's my intuition.
But then if you put a massive insertion in a CFT, you get something which is not critical anymore. So you get a gap theory. If you put a mass in a CFT, you get a gap theory.
Well, this is a one-dimensional, I don't know enough about it, but this is a one-dimensional CFT. Not the two-dimensional one. I don't know if it holds also for a one-dimensional CFT.
Well, maybe I'm completely confused, but in my understanding, if you put a mass in a CFT, then this mass flows under RG, so you get a gap theory, you get something which is not a dilation invariant anymore.
Yeah, but again, well, the statement I am making is at the level of a low energy limit. So something that is not even conformal, that breaks conformal invariance, because the Schwarzschild is exactly the mode that breaks conformal invariance at the boundary of the disk, of the hyperbolic disk. So this is something that breaks conformal invariance, but in the ultraviolet limit would become something that is a CFT in one dimension. So yeah, the guess I am making is at the level of the Schwarzschild, and the Schwarzschild is not CFT. It's not a full UV complete theory. So yeah, that is another question. What does it happen actually when you consider the whole CFT? Yeah.
Yeah, let's check.
Okay.
Thank you.